Hi, so Griffiths Quantum Mechanics problem 5.34. We're going to calculate the Fermi energy for non-interacting electrons in a two-dimensional infinite square well. We're going to let sigma be the number of free electrons per unit area. Alright, so we're basically just going to look at, back in section 5.3, Griffiths goes through this for 3 dimensions. We're just going to look at it in 2 dimensions. So if we look at the say in K space of a Kx and a Ky, right? So rather than a 3-dimensional grid, now we're going to just have a 2-dimensional grid, right? And there, instead of one sort of cube per state, or I guess 2 states if you count spin, there's just going to be a square. All right, so they'll kind of fill up like this, right? And then you'll get they start from this this corner, and they just kind of build up. All right, and you'll end up, rather than a spherical surface, which they reach, in the end, you'll just end up with, this is looking nice and ugly, but the maximum that you'll reach will just be an arc of a piece of a circle, all right, in 2 dimensions. Okay, so rather than looking at the volume in K space for each one of these states, well, I guess it is still, it's a 2-dimensional volume, which is an area. So so basically this is built off of equations 5.40 down through 5.43, and in 2 dimensions the volume of each of these little cells in K space is going to be pi squared divided by Lx times Ly. Alright, so for 3 dimensions this was pi cubed divided by Lx times Ly times Lz. Alright, and we're just going to call this pi squared over A. Alright, and this was a V for 3 dimensions. Alright, so so this is the volume of one of those little cells, right? That's each going to hold 2 electrons. And so if we were to add up these little cells, what we would have the all right, pi squared over A. All right, and then on the other hand, we're looking at what is the, rather than the, in 3 dimensions it was an octant of a sphere, because we're only looking at positive K's, right? So that's why it's not the whole sphere, because the K's don't go below 0. So only for positive K's. So for 3 dimensions, we're looking at the octant of a sphere. For 2 dimensions, we're just going to look at this quadrant of a circle. All right, so the area of a quadrant of a circle, rather than 1/8 times the volume of the sphere in 3 dimensions, we'll have 1/4 times the area of a circle in 2 dimensions. All right, so this is going to be equal to 1/4 times pi kf squared. So this is in 2 dimensions. All right, kf is the radius out to the edge of these states. All right, so I drew this really jagged, but you can kind of think of this as building with Legos or something, right? You're trying to approximate a curved surface with a bunch of Legos. If you've seen pictures of this sort of thing, they're very good at, the more Legos you use, the better you can approximate a surface. So I don't know what the numbers would look like if we had a mole of Legos. I don't know how much that would be, but just for the sake of argument, say we had a ball of Legos the size of the moon or something, right? Basically, with that many Legos, you can fill in straight out, and there's no appreciable difference between the jaggedy surface of the Legos and this perfectly round surface of the sphere, or in this case of this quadrant of a circle. All right. So Griffiths deals with this in the footnote 14. Okay. All right. All right. So this Fermi, this K at the Fermi energy, right, is just is the radius of this. Okay. So all of this hinges on this being equal to this. Okay. So now to find let's just take another sheet. The Fermi energy, right? H bar squared K sub F squared over 2m. All right. So all we have to do is solve this for Kf squared and plug it into this. So I get an H bar squared. It's an H bar. Kind of a mess. Over 2m. All right. So now just multiply both sides by 4. So we get a 2n cubed. And let's see, we divide, one of these pi's goes away, so we just have 1 pi. And over a. Okay. I don't think I left anything out. All right. So these 2's can cancel. So we're just left with a pi h bar squared over m, and then we have our n q over a. Okay, so and then again let me see exactly what we call this, the number of free electrons per unit area. Okay, Q, we need to remember what Q was. Q was how many electrons are donated to this electron gas per atom. All right, so per one of these cells, or whatever. I guess the cells are states in K space. But yeah, so each atom contributes Q free electrons. N is the number of atoms. All right. So anyway, basically this here is the number of electrons. Okay, so that divided by A is just equal to sigma. All right, so we have pi h bar squared sigma over